Hello everyone. In this video, we will discuss an application on the F statements that were covered in the previous video. So this is a classic example in science that gives an immediate application on F statements. So let's see. We are asking you to write a MATLAB script that reads the coefficients of a second order polynomial. That's the general form of the second order polynomial, ax squared plus bx plus c equals 0, and tells the user if the roots are real, imaginary, or repeated reals. And then there is a hint here about making sure that we address the issue of checking the equality of real numbers correct. So let's take this, step by step and see uh, how can we analyze this problem. Let's just remember together that the solution for this second order, the roots are negative b plus or minus root b squared minus 4ac divided by 2. But we don't really need to calculate the roots. I mean, it would be a waste of time to actually calculate the roots and decide whether complex or not. There is, if you remember the theory of second order polynomials, the roots of second order polynomials, all what you need to compute is just the so-called discriminant, which is this quantity here in the bracket. So all what we need to calculate is b squared minus 4ac. And that is enough to decide the nature of the roots. So let's analyze the different cases. If this is greater than 0, so that actually means that the roots are real. And we can remind you that graphically this looks like this, maybe a second order polynomial that's like this, or maybe one like this. And this is a root and this is a root for this polynomial, or this is a root and this is a root for this polynomial. The other alternative is that b squared minus 4ac equals 0. And in that case, we have a second order polynomial that's barely touching the x-axis in one point. And this is the case of repeated reals or repeated reals. So a classic example for this, let's say x minus 1 square equals 0. And this leaves us with the third possibility, and that's the case of less than 0. And in that case, of course, because you are taking the square root of a negative number, you will have complex roots. And, an example for this, something that doesn't intersect with the x-axis, something along these lines. So these are all the three possibilities. So it all depends on the value of b squared minus 4ac. So let's actually start preparing the programming. We don't need to resolve everything now. Let's just get things up and running first. I'm going to save this as symbol or, roots of a second order polynomial and f statement. So this is an application on f statement. So obviously, to do this branching, we need to do an f statement. So let's start by getting the ABC from the user. So A equal input, maybe please enter A. And, we can speed up things a little bit by taking this as a copy. A semicolon here will suppress rewriting this on the command window. So I have B, input, please enter B. And, similarly, C, please enter C. All right, we got our ABC. It's also good at this stage to calculate the discriminant. And I can give it any name. For example, I can call it disk. Also, we would benefit from a comment here, calculating the discriminant. And disk equals b squared minus 4 times a times c. Please don't forget the times, right? Don't write this for ac. Now we need to do the branching. We need to do the f statement. So there is an f statement, and obviously there is an n. So every f comes with an n. But let's be careful a little bit, because we are asked to make sure that we address the issue of checking the equality of real numbers correctly. Remember, um, you need to check equality with 0 to decide whether the roots are repeated reals or not. And we remember a discussion from a previous video that checking the equality of the 0 doesn't actually work using the double equal sign. And in general, the p squared minus 4ac will be a real number or a float. So let's see how we will address this. So to check the equality of p squared minus 4ac equals 0, and we decided to call it the discriminant, we need to show that the absolute value of the discriminant minus 0, and again absolute value because we need the difference, we don't care about the sign, is less than some small number. And if you review our video, our previous video on checking the equality of real numbers, we recommend this to be 10 raised to power negative 14. And if you actually rewrite this, it will be, because I can cancel minus 0 here, is just the absolute of the discriminant is less than 10 raised to power negative 14, and that's checking the equality. But here we will discuss a very, very subtle point that is not really obvious from a first time. Which condition we put first? Should we check the greater than first, or the less than first, or the equality first? Here is the recommendation, and it's a little bit a subtle point, but it's also related to round-off error. The problem is, you might have a number, a discriminant, that's, let's say, 0.000001, or maybe smaller than this. Let's actually say 10 negative 10 negative 17. So that's the value of the discriminant. But then if you put the checking that the discriminant is greater than 0 first, obviously 10 raised to power negative 17 is considered greater than 0, and then MATLAB will tell you, yes, it's greater than 0, so these two roots are real and different. But there is a problem here. We said that we can't, within the capabilities of round-off, or within the issue of round-off, to discriminate between two numbers whose difference is 10 to the negative 17. That's too small. And in fact, if the difference is 10 raised to power negative 17, for all practical purposes, these two numbers should be considered equal. And as such, we should check equality first, right? And then we check greater than. So in other words, what I need to do here is to check that the absolute value of discriminant is less than small number, we said negative 14. And if this is the case, I will display a message for the user saying, these are two repeated roots. They are real also. So that's one case. Else F. Now it's equally fine to put greater than or less than. It doesn't matter. So remember, the whole idea of checking the equality first is to avoid having some very small number, either greater than 0 or less than 0 at the beginning. Because if I put the greater than, let me go back, if I put the greater than check first, then it could be greater than by 10 negative 17 or negative 18. And obviously this shouldn't be considered greater than 0. This is within the accuracy of the computer, is 0 for all practical purposes. And because of this, it is better to check the equality first. And this is a general rule of thumb. It is for real numbers. If you want to branch out between greater, less, or equal to some number, it doesn't have to be 0, by the way, let's say in another problem, then it's better to check the equality first, and then it doesn't matter to check positive or negative later. So it's equal. Okay, so else F, the discriminant is greater than 0 then in this case, I will display a message that these are two real, or maybe I can say also two different real. And finally, by the way, the last one I could put else, or I could put um, else f. So both of them are fine. Let's go with else f. The discriminant is less than 0. Then display two complex roots. No code is finished before we actually test it. So let's do a quick test here. Very simple tests. Um, let's actually take, let's see, let's come up with some simple examples here. Let's say x squared plus 1 equals 0. Obviously, we know here that the roots are complex. So let me run. A is 1, b is 0, the coefficient of x, and the coefficient of x power 0 is 1 here. And why there is an error here? Did we make a mistake somewhere? Why it says, oh, we made a mistake. It says, oh yeah, this has to be disk. Sorry, we should have corrected this. Good, 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 good that we made this mistake. So let's run again. 1, 0, and 1. And yes, two complex roots. Let's do another test case just to confirm. We can do other simple test case. Let's say x squared minus 1 is 0. So obviously these are two different roots, different and real. So a is 1, b is 0, negative 1. So these are two different real. Let's try to come up with equal roots. So something like this. So this is going to be, let's see, it's going to be x squared minus 2x plus 1 equals 0. So let me run again the code. CLC will help us to see what's going on. So a is 1, b is negative 2, and c is 1. So two repeated real roots. So thank you so much, and see you in another video.